just frustrated that it pisses me off that Fairfax County has access to Google, but then they limit its power. So I'm using my account, I wrote a note saying that started one. Because I'm just getting like kids are emailing left and right, this show that came on the one lesson. I'm sorry I yelled at you. Okay. Sorry that I'm so late with this. I had to tutor today, and then I was late getting back, and I needed to eat food because I was grumpy, and you don't want a grumpy teacher teaching you calculus. All right, let's see. Let's get this up here. Okay, so all right, here's a plan. Instead of doing the next lesson, because I know the next lesson, students tend to have lots of questions. We're going to look at the lesson after the next lesson, because it's actually not too difficult, and it uses a lot of ideas that we've already looked at. So keep in mind, this is not on the quiz. This is just a lesson that's coming after the quiz. We're just taking the initiative and using the available time that we have today to sort of stay on track by doing one of these lessons. So what we're going to talk about today is improper integrals. And what an improper integral is any integral that's evaluated either to infinity or at some point of discontinuity. Okay, so for example, let's look at the integral from 1 to infinity of 1 over x dx. So how would we evaluate this integral? Well, if we think about the integral as the area under the curve, well, that area looks to be infinite, okay? But maybe it's calculable. I don't know, but let's find out, okay? So there is a way that we can calculate this. So we'll integrate typically, or excuse me, what we'll do is replace the infinity sign or any of the places of discontinuity, in this case, the infinity sign, with some variable. T is what's typically used for this method of integration. And then what we'll do is evaluate this integral and then look at the limit as t goes to infinity. Okay, so we'll get some expression with t's in it, and then that expression will evaluate as t goes to infinity. So the integral of 1 over x is natural log of x evaluated from t to 1 is the natural log of t minus the natural log of 1. Okay. Now the limit as t goes to infinity of this, well, the natural log of 1 is 0, and the limit as t goes to infinity of the natural log of t, well, natural log of t looks like this. That goes to infinity. So we get something like infinity minus 0, which is not a number. Okay. So we say that this integral is divergent. Divergent. Yes, divergent. Okay. Meaning that the sum of the subsections as we go, in this case, out to infinity, is divergent. We keep adding things and adding things and adding things and adding things, and we never get to a point where we're adding so little that we consider it like adding nothing, and therefore this limit doesn't exist, or excuse me, this integral doesn't exist. The integral is considered divergent. Had we gotten a number here, this integral would then be considered convergent. So let's look at an example of what a convergent improper integral is. Now, for those 8 or 9 of you, how much? Oh, 10 now. Those 10 of you who are logged on, I'm not sure how the question and answer feature of Hangouts works. But if you do have a question, I think you can type it in there, and I'll see it and be able to answer it, because it's hard for me to be on email at the same time that I'm doing this. So, okay, next example, something a little bit more familiar, or recent at least, x e to the x dx. And we want to evaluate this from negative infinity to 0. Okay, now x times e to the x. This integral has to be evaluated using integration by parts. Okay, so the first thing that we're going to do is replace the infinity sign with constant, or excuse me, some placeholder. Like I said, t is what I typically use. Oops. T is not going to infinity this time. T is going to negative infinity. Okay, so like I said, this has to be evaluated using integration by parts, and luckily for us that this can be done using the lattice. So u dv, make u x 1 0, dv will be e to the x, e to the x, e to the x, plus minus plus. Nice little review for your quiz there, right? So this integral gets evaluated as x e to the x minus e to the x from t to 0. All right. Well, we plug in 0, we get 0 here, but 1 here. It's a negative 1, so keep that in mind. So negative 1 minus, plug in t. T e to the t minus e to the t. All right. So now we just have to look at what happens to this expression as we take the limit of t going to negative infinity. Okay. So let's see. I'm going to rewrite this a little bit. How about I rewrite it over here? So the limit is t goes to negative infinity of, I want to pull out like an e to the t. E to the t 1 minus t minus 1. That looks better to me. Okay. So let's see. E to the negative t. E to the negative infinity is 0, right? Because e looks like that, or e to the x looks like that, and as we go to negative infinity, this goes to 0, right? So this equals 0, and I'm left with negative 1. So my initial integral here is evaluated to negative 1 and is therefore convergent. The integral converges to -1. Okay. Now, I like that problem because it had integration by parts, which is a nice, like I said, review for the quiz that's coming up. And then it does make you think about limits again, right? Back from Unit 1 and Unit 2, we haven't really thought of limits in a computational sense, merely as a conceptual idea, because limits are involved in both their differentiation and integration. We just haven't done a definition kind of problem in a while, so limits haven't come up. But I like this because it brings limits back into play and gets you to think again about what these functions do, you know, at infinity, which is important. So let me see. No school tomorrow, says Michael McClellan. I don't know who that is, but I don't have an email. So, I don't know. I don't see any other questions. So we'll move on. Okay. So you can see why I chose to teach this lesson online, because it's a little more straightforward. The other lesson that was supposed to be taught today was a little bit more conceptual, and actually has lots of computation involved. Okay, evaluate. Integral from -infinity to +infinity. 1 over 1 plus x squared dx. Now this isn't one that we would have to do this for, but be prepared on your test on the AP to have to use improper integration on a problem with which you would have to use partial fraction decomposition to simplify. You know, that's a possibility. Any combination of the techniques that we've talked about in this chapter are fair game for the test and definitely for the AP exam. Okay, so let's see. This function has an asymptote at doesn't have an asymptote. It has a horizontal asymptote, y equals 0. But in order to evaluate with two limits of, or two bounds of infinity, I can't take like a double limit of something, right? I can't say like the limit after I evaluate this, the limit as a and t go to positive infinity and negative infinity. That doesn't make sense. So what we'll have to do is we will break this up. And we'll break this up into the limit as t goes to infinity. We'll do negative infinity because we want to do t to 0. And it doesn't matter where the fact that I used 0, I could have used 1, but I used 0 because 0 is something that's really easy to plug into other things. And then to that, we will add the limit as a goes to positive infinity from 0 to a of 1 over 1 plus x squared dx. Now, we can see that The two integrals here just split up from the original integral, and I split it at 0, and I'm adding them together. And then I replace the negative infinity with a t, and I'm taking the limit as t goes to negative infinity, and I replace the infinity with an a, and I'm taking the limit of that second part as a goes to infinity. And now I just have to do these two problems separately here and then add the results. So both of these integrate nicely to arctangent. Okay. So we'll end up with arctan from t to 0 plus arctan from 0 to a. Forgot my limit over here. Okay. And then we need to evaluate. So let's see. Arctan of 0 is 0. Right? Let's double check here. Tangent. Arctan. Yeah. So arctan of 0 is 0 minus arctan of t. I just had deja vu for some reason. I don't know why. Like I've taught this lesson before from this very spot. Again, arctan of 0 is 0. So we just have a negative arctan of t. We plug in infinity, negative infinity. Well, let's see. Arctan is bounded above and below by pi over 2. So as we go to negative infinity, we approach negative pi over 2. So negative pi over 2 gives me a positive pi over 2 plus as a goes to positive, as arctan goes to positive infinity, I approach pi over 2. So this becomes pi. And that's quite an interesting result there. Quite an interesting result, right? To have something rational like this end up being, first of all, convergent. We're adding up an infinite number of segments, right? An infinite number of area, and to get something like pi is pretty, it's pretty outstanding, right? Still no. Oh, Alice, can you solve this if you don't know what the graph of arctan is? Yes, you don't have to know what the graph of arctan is, but you do need to know what the value of arctan of 0 is and the arctan of pi over 2 is. So makes it easier. Otherwise, you're just memorizing facts and figures. But if you know what tangent looks like, right, and you know it's bounded here and here at negative pi over 2 and pi over 2, when you find the inverse of something, you're just reflecting it over the line y equals x. So if you were to do that, sort of get this scenario that looks like this, right? And now these vertical bounds have become horizontal bounds. Now, I have to run and grab my charger real quick before my computer turns off. All right, we're back. Cutting it close. 2%. Oh no. All right. Okay. Okay, so Alice, I hope that answers your question. That's a good question, though. But yeah, you really, I mean, it's one of those things I'm going to say that at this stage in your mathematics career, you should know what tangent looks like, and you should be able to go from taking a piece of tangent, right, and flipping its domains and ranges, because that's what you do when you take the inverse of something. The arctan is just the inverse of tangent, and if the bounds of the domain are negative pi over 2 to pi over 2, then the bounds of the range of the inverse have to be the same thing. Okay. So, okay, done with that. We're good. Okay, moving on. We're almost done, guys. We got 2 more examples to do. Okay. Integral. Ugh, it's a horrible integral sign. From 2 to 5 of 1 over the square root of x minus 2. From 2 to 5, 1 over the square root of x minus 2. Okay, so I know what you're thinking. You're thinking, Mr. Southard, you said this was a lesson about improper integration, and I don't see any infinity signs here. I'm not evaluating at infinity. So what's the problem? The problem is that if I plug 2 in here, the function's undefined. So we do need to know what this looks like, and that's going to look something like something like this. Okay. And now how do I know that? How do I know that that's what it's going to look like? Well, x can't be anything less than 2. Has to be 2 or greater, right? Has to be, actually can't be 2. Has to be greater than 2. Okay. So x values have to be greater than 2, and as my x values increase, my y values are going to increase. Simple as that. I know that that means that the graph's not going to go below the y-axis or the x-axis. So I don't know, it might be a little more like this, or maybe it's even like this. Who knows? It doesn't matter. The point is that really close to 2, it looks like that. Okay. So what I'm going to have to do here is take the limit as t goes to 2 from the positive direction. Does it make a difference when you're doing the computation? No, but it makes a difference when you write it down on your test, because this is right and that is wrong. You can't take the limit of this as you're going from the left and the right. It doesn't exist, but it does from the right. Okay.
Okay, so we need to integrate. This is going to end up being something like 2 times the square root of x minus 2. We're going from t to 5. How'd I get that? U substitution in my head. I take the derivative of this. It's going to be 1/2 times, that gets rid of the 2. X minus 2 to the negative 1/2 drops it into the denominator. So I'm just doing that chain rule in reverse in my head. I mean, if you need to take the time, let's let u equal x minus 2. du is going to be 1 dx. Great. And then you're really just integrating 1 over the square root of u du. So you can do that if you need, but we're getting to the point where you need to be able to jump from here to here, especially being BC students. So let's see, 5 minus 3, 5 minus 2 is 3. So we have 2 square roots of 3 minus 2t minus 2. Okay. Ooh, you know what? I think I drew that wrong, but it's okay. All right, so now, obviously this is going to be 2 square roots of 3, but what is this going to come out to be? What is this going to be when I approach t from the positive side? Well, this is going to look like a square root function shifted over 2 and stretched by 2. 1, 2. Stretch it by 2. It doesn't even matter. Okay? As I come from that direction, I'm going to approach 0. Okay? So I get 2 square roots of 3 as my answer, and that this is convergent. Now, the reason I'm writing convergent and divergent on all these because I want you to get used to using those words, because when we get into Taylor series and infinite series, Maclaurin series, things like that, we're going to be using the words convergent and divergent, and this is one of the tests that we'll use to test whether those series are convergent and divergent, and they have very similar, the results of that test are very similar to, the outcomes are very similar to what we're doing. So you don't need to write that it's convergent or divergent unless I ask for it. I'm just writing this because in some of your homework problems, the question merely states determine whether the integral is convergent or divergent. And so yes, you do have to determine whether there is an answer, but it's not the answer or the value that I'm interested in. I'm merely interested in whether it's convergent or divergent. And there is no real quick way to determine that yet. We'll get to that. I don't see any questions that have popped up. So let's see. Let's move on. We have one more problem to look at, and then we're going to call it quits for the day. And we'll talk about future. Well, we can do that while I'm writing this problem up. I don't see us being in school tomorrow. However, like I said, we have to operate under the assumption as of now that we will be in school tomorrow until the call has been made. With that, the quiz will still be Thursday. It will still only cover the material that we talked about. I posted all of the homework solutions and all of the in-class lessons, both blanks and filled in and completed notes on Blackboard for you to study from. Let's assume we are in school tomorrow, then I'll be after school. If we're not in school tomorrow, then I'll be in school early on Thursday. So if you need any additional support, I can be there before your quiz. One more here. Okay, the integral from 0 to 3 of 1 over x minus 1. Now, if we're out of school Thursday, I'll teach online again. I'll teach the lesson that I was going to teach today, but I'll be a little more prepared. And it's a short lesson. It's just a lot to take in conceptually. That is. This one, I don't think there is as much to take in conceptually, so I was okay with teaching this one sort of on the fly. All right. So what's the problem? I'm telling you this is an improper integral because it's in the lesson for the day about improper integrals. However, I'm not evaluating at one of the endpoints being infinity or negative infinity, and neither of the endpoints makes the denominator 0 or makes the function undefined. So what's going on? Well, let's assume that there isn't anything going on. We would integrate this and we'd get the natural log of x minus 1 from 0 to 3 and we get the natural log of 2 minus the natural log of negative 1, which we don't like, but I might get to this and think there's something off about this. Well, if you think about the graph, which you guys spent most of your Algebra 2 careers looking at, I want the integral from here to here. So I'm evaluating over an asymptote. That's where the improperness has come into play. So again, yes, you need to know what that graph looks like. So we're going to break this up and do the integral from 0 to t of 1 over x minus 1 dx as the limit as t goes to the asymptote 1 from the negative side, plus the limit as a goes to 1 from the positive side, the integral from a to 3, 1 over x minus 1 dx. All right, so we get the natural log of x minus 1 from 0 to t. Limit as t approaches 1 from the negative direction, plus the limit as a goes to 1 from the positive direction of natural log x minus 1 from A to 3. Okay. The limit as t goes to 1 from the negative direction of the natural log of t minus 1 minus the natural log of negative 1 plus the limit as a goes to 1 from the positive direction. Natural log of 2 minus the natural log of a minus 1. Okay. So let's see. This. The natural log of t minus 1 takes that asymptote and moves it over to there. So let's see, the natural log, this we can approach 1 from the negative direction. So this does not exist. We know that does not exist. This is the natural log of 2. And that is going to be a negative infinity. Well, that's a mess. It's divergent. Does not exist minus does not exist plus a natural log of 2 minus negative infinity. That's divergent. That's divergent if I've ever seen it. So this would be a method for showing that this is divergent. What I did initially by just evaluating the integral and getting non-existent answer doesn't suffice. It needs to be rigorous. It needs to make mathematical sense. You cannot evaluate an integral over an asymptote. And I know it seems like a lot of work to get to something that we maybe could have reasoned ourselves, but no, it works. Shows that it's divergent. We get a mess. Haven't broken any mathematical rules. So there it is. So like I said, that's the lesson for today. I will either see you tomorrow, either after school or during school. Quiz Thursday as of now. If we're out of school Wednesday, I'll be in school early Thursday. If we're out of school Thursday, quiz next week. And class on Thursday. So thanks for those of you who tuned in. And for those of you who are watching on YouTube later, if you have any questions, shoot me an email.